Good afternoon. Welcome back to ECE 207. The pile is getting larger. I should say the stack. The stack of papers is getting larger for homework number 7. You know, I hope by now that there's the third exam on our next meeting day, which is Thursday, and it will not be postponed like the other one. We want to make sure and enjoy our Thanksgiving week, so we won't have an exam during that. Now, I don't want to keep, well, I hope to see you in a week, actually, right before, yeah, that's not happening, huh? Well, I'll be here, and for those of you that are having trouble getting home in the snow, you can be with me. We have to worry about that here. Tomorrow I'm having a few more office hours than normal. Today's were pretty packed in terms of customers, and maybe I won't expect quite as many tomorrow, but maybe there will be. I think there was a frantic push to try to understand the homework. I'll try to get the homework solutions prepared and posted. What I may do is a few of those I might actually work via video and post those and help have those in addition to the old exam worked problems that are there on the website. Today we have a pretty full menu in front of us. Takes up more than a page. Let's first begin by talking about the op-amp analysis process or procedure just in general. Then we'll look at determining negative feedback, and you should be able to do that on the exam. Look at a circuit and say, yes, it's negative feedback, no, it's positive feedback. If it's positive feedback, you should be able to do the analysis to determine which supply value, either the positive supply rail or the negative supply rail that's locked at or stuck at, depending on the input. I don't know if we will work through all of these, but here are some examples to help us try to understand or get a little bit more comfortable working these op-amp problems. I'll try to talk about open loop versus closed loop in that process as far as what that really means, if that's still not clear to you. We'll look at op-amp limitations, which are saturation that I'll talk about today, saturation, output current limit, slew rate limit, and full power bandwidth. Those were on your homework, and those are important for exam purposes. We'll talk about, well, actually, I think you realize we're not going to get to the dessert on the menu, which is the bottom two, whether you want the amplifier characteristics or the input-output impedances. I don't know which you prefer. I don't know what the special is today, but we'll probably run out of time, and those are available. Some discussion, general discussion on amplifier behavior and properties are back in Chapter 11, and they're in Section 5 and Section 6 of Chapter 11, and you can then look at that to help maybe better understand what they're talking about when they're referring to why do I want a high input impedance, why do I want a low input impedance, what's the difference, why would I be interested in that. You're probably more interested in exam number 3, but that material will be on exam number 3. This is now posted on the D2L website under the handouts section. This menu is just about as long as today's class, but you should be comfortable on item 10 analyzing or determining what kind of amplifier you might have, whether that's an inverting or a non-inverting, whether you have summing or differencing going on, whether you have this particular, did I put it up there? I wanted to, but maybe I didn't. Item G, inverting or non-inverting. Do you remember that from the homework? That was the switch, whether that switch was open or closed. Converted this particular signal or this circuit into a inverting or non-inverting amplifier configuration. You also need to understand the op-amp limitations. I'm also giving you a verbal description of what it means to, if I could read, on item 4, it talks about negative feedback. And we'll talk a little bit about that in class today, but the general idea is if you have a resistor network, a network of resistors, that means one or several that might be grounded between the output terminal and the inverting terminal on your op-amp, that means you typically are going to be in negative feedback. That's all you have to look for. It doesn't matter if that negative terminal is sketched to be above or below in your diagram the positive terminal. It's the fact that you're going to the negative terminal or the inverting terminal on your op-amp that constitutes negative feedback. Conversely, if you have just the opposite, you have positive feedback, meaning if your output is connected back to via some resistor network to your non-inverting input, that's going to give rise to positive feedback. And once you're in positive feedback, you really only have one of two possible outputs. You're either at the positive supply rail or the negative supply rail, and what that rail is depends on how much you're getting when you plug in your toaster, or what is the power positive supply value. If that's 4 volts, it's 10 volts. If it's plus 15 volts, that's what you would be stuck on. And we'll talk a little bit more about that as we get through today's class, I hope, or as we work through the material. Let's get started on our 3-hour lecture for today. And the first thing that I wanted to talk about was the op-amp analysis approach. If it doesn't make sense from what I'm saying, maybe you could look at, and now I can't even read my own writing, it's in chapter 14, but I think that puts us up into the 700s, possibly at the end of the chapter. On page 708, if you look at, I know that you studious individuals have memorized the summary bullets at the end of the chapter. This is summary item number 4. All I have to do is refer to a number and you know what I'm talking about. If you now look at that summary item, it talks about how you might analyze an op-amp in general. Let me just briefly say that the first thing you might want to do is check to see if you have negative feedback. If you do or don't, that's going to basically influence your next modes or your subsequent decisions in your analysis process. Negative feedback is as simple as, is my output connected back through some resistors to my inverting terminal on the input side of my op-amp? Boom, negative feedback. Let's make some assumptions. And then if you're in saturation, you'll have to go back and change your work. But we'll talk about that later. Once you know you have negative feedback, you can use SPC. Did anyone get that in their text messaging over the last week? SPC. Everybody send that to somebody. What's your SPC? The summing point constraint, which means the difference voltage, that V sub D, the voltage between your non-inverting and inverting input terminals on your op-amp is 0. And we always are in this class assuming that the input currents, the currents going into the input nodes of your circuit or in your op-amp are 0. That's what we collect into this summing point constraint. And then we simply use circuit analysis. I think you know what I mean by that. KVL and KCL, and we actually start alternating between these probably. We start doing KVL, then KCL, KVL, KCL, and we just sort of sequence through, and we sequence through in a manner that essentially we work from the input side of our circuit to the output side. And we do that working in a way that we try to, when we start writing these KVL loops, you probably don't want to make them really, really big, meaning you don't want to go through a lot of different elements before you return to where you started. What you want to do is, if you have the chance, drop to ground as quickly as possible, and the reason you're doing that is to try to minimize the number of unknowns in your mesh equation. So in the KVL, what I'm going to say is go to ground instead of creating big KVL loops. And I'll try to indicate what that means as we go. Let's now look at, now I've forgotten my menu, I didn't write it down. I'll have to ask the waiter or somebody to remind me what the menu was. What was our goal list? That was our first goal, wasn't it? Now let's talk about, so this was discussing the op-amp analysis process. Let's look at negative feedback and positive feedback. If I sketch the following, those little triangles are meant to be ground points that are at the bottom of my page, and I might label these resistors, maybe that's R sub F and that's R sub 1. The R sub F, the F is for feedback, and we are feeding back from that output signal, V naught, through that resistor back to, and which terminal are we feeding that information back to? The inverting terminal. Because of that yellow highlighted connection or interconnection, this is actually negative feedback. And boom, we're done. Now we can go on with the analysis. Question?
Is that what you're calling a supply rail?
No, I'm not calling that a supply rail. That's a valid question. Where is my supply rail? My supply rail is not even shown. That's the problem with these problems, is that we're assuming that you remember that these are, that your toaster is plugged in. And 10 and minus 10 are just convenient. That's going to depend on what you want to have there. Somebody else might say, oh, for my problem, I actually want minus 4 and plus 4. They don't even have to be symmetric. This could be 0 and this could be 8. You just want the negative supply rail to be less than the positive supply rail. Those three colors, black, blue, and red, oh boy, you'll be black and blue after the exam Thursday. Hopefully not. Hopefully you won't be bleeding, and hopefully I won't be turning the exam red after you turn it in with my marks. But Each of those colors indicates potential or possible supply rails. And those typically aren't even shown. They may be stated in the problem, they may not be. And on an exam, if it's not stated, you might have to say, oh, I'm going to assume the supply rails, the positive is 10 volts and the negative is minus 10 volts. And I'm going to work it with that if you need that information. Question?
Where does it go in, like when will you use those numbers?
When will you use those numbers? You use those numbers when you look at your output voltage and you say, am I exceeding my supply values? If, for example, your V input was 1 volt, I'm going to use simple numbers, and let's say your supply rails were plus and minus 2. Then if your gain in your circuit, what kind of a circuit is this anyway? This is an inverting, this is a classical inverting op amp. Let's say that R sub F and R sub 1 were selected to give us a gain of 3. Now we have a gain of 3, we have an input of 1 volt. What's our expected output? 3 volts. Is that bigger than our supply rails? What was our supply? Plus and minus 2. So is 3 bigger than 2? Yes. So we're going to saturate. We're going to go up and we're going to hit 2 and we're going to go flat. And then we're going to come down if it's a sinusoidal input signal, Vn, that has an amplitude of 1. It's going to want to produce an output of 3, but it can't. It can't go beyond what we're supplying. And that's our toaster that I keep plugging in. Now, if our supply rails were set to plus and minus 10, we could do that. We could go plus and minus 3, plus and minus 3, because we're not getting above 10, plus or minus 10. Question?
So does that mean that our output voltage is 2?
That means it depends on what the input is. If our input was a sinusoid, it would be oscillating between plus 2 and minus 2. And it would go, would look like a sine wave until it got to 2, and then it would clip. It's what's called clipping. And it will clip and be stuck at 2. Then it'll come down, and then it'll be clipped at minus 2, and it'll go flat across minus 2. Then it'll come back up and clip at plus 2. Does that make sense? Question?
Shouldn't B sub CC be negative and B sub EE be positive?
I don't know. Maybe my notation is wrong. The question was, should VCC be negative and VEE be positive? I was thinking VCC was the positive, but my thought or my memory may be 180 degrees out of phase.
I think he's referring to where your minus and your positive sign are.
Oh, are you referring to the minus and plus terminals on the input side?
Yeah, doesn't that correlate?
No, it doesn't really correlate. So the question was, does the supply, in the diagram, so what you want me to do is relabel this and put VCC next to the plus and VEE next to the minus. I'm going to say it doesn't really matter as long as you make sure that when you plug your little chip in, that whichever pin corresponds to VCC, you make sure that that's more positive than the VEE pin. And that's maybe pins 4 and 7 or something, and your output might be pin 3. Does that answer your question? So it's not critical in the drawing because what? I typically haven't even shown those.
But next to the inverting input, the negative on the left part of it,
Next to the inverting input,
there's a negative sign there. So you have circled yellow highlighted.
yes, so that just means that's my inverting input terminal. That has nothing to do with my supplies.
Oh,
So my supplies are independent of my input terminals. And my supply values of VCC and VEE, that's how I plug my toaster in. You get up in the morning, you want some toast, you put your toast in a toaster that's not plugged in, what's going to happen? Nothing. Here you're walking up, you put something into this op amp, and you haven't plugged it in, what's going to happen? Nothing. So you have to plug it in, and a lot of times that's not even indicated. But you plug it in with these supply values. And those can be adjusted or set to whatever you decide it needs to be. Questions? Wow, that was negative. Question?
Yeah. So you have symmetric
Okay, so now the question was, what if we made it 0 and 4 in terms of the supply rails, and I still wanted to go between -3 and +3? Is that true? So now let's say I still have my circuit designed to give me a gain of 3, and I'm inputting a 1 for my input voltage. It's wanting to go between plus and -3. But my supplies are restricted to 0 and whatever you said, 4. So the top half is going to look fine. The bottom half is going to be stuck at 0. So you go blip, stuck, blip, stuck. Does that make sense? You'll clip at whatever value your supplies are not, or that your supplies are exceeded at. Let's look at some other examples. Suppose I drew something like this. Positive or negative feedback? Anybody got a coin? Flip it.
Negative.
It better be a 4 or 5-sided coin if these are multiple choice, right? Come on, do better than, no. What do you think it is? It's negative, right? Because I have a resistor that's connecting the output terminal to the inverting terminal. It doesn't matter that the inverting terminal this time is drawn on the minus or on the bottom versus the top. This is also negative feedback. Which means that this voltage, V sub D, is now 0. That's what we can assume during our analysis. If it turns out that V0 exceeds, so here's where I'm getting, let's say this is VCC is equal to plus 5, and this VEE is equal to minus 4. Suppose V naught, after your calculation, you go, oh, V naught, based on the magnitude of Vn and my gain, it should be plus 7. You look and you go, wait a minute, plus 7 exceeds VCC. It's actually going to saturate at plus 5, and your V naught will be 5. It won't be 7. Does that make sense? Even though you'll have negative feedback, but you're going to be saturating your op-amp. What about the next circuit? What if we had the following? Positive or negative feedback? Positive. I think everybody's getting this, right? Let's then move on. Before I move into a problem or a circuit analysis, let's talk about open loop versus closed loop. Maybe I'm getting, or is it clear to everyone at this point after your homework what we mean? These terms are just thrown around like you know exactly what's being stated. What we're needing to know in this case, in this class, that is open loop. Nothing is being fed back. We simply have something applied to the input terminals, and that goes open loop to the output terminals, V naught. What is V naught? but it's probably going to saturate if that difference, if that V sub D is very big, because what is A sub OL? Ideally, it's infinite. In reality, it's 10 to the 4th or 10 to the 5th or 10 to the 6th, and it's not very repeatable in manufacturing processes. So it's now 100,000. This guy's not very big then before you would be driven into saturation. That's why we seldom use an op-amp in an open loop configuration. But if it was such that this would be, let's say, VCC, and this is minus VEE. And if VCC is 10, you can see that this particular value here, or maybe I should call this V difference, which is what this is, and this slope and that OL is open loop. That's our open loop gain. That's really, really steep. And this distance is not very big. That's in the whatever 10 divided by 10 to the 5th is. Okay, 10 to the minus 4th. Now we're less than millivolts in terms of V sub D. It can't be very big before you would saturate in this open loop configuration. That's why most of the time we're not dealing with open loop circuits. If you simply want to be switching between the positive rail and the negative rail, maybe you would operate this way and just use it as a switch. But closed loop means, and I hope by now you're comfortable with the plus or minus being on the top or on the bottom. It really doesn't matter. You just need to make sure that you're interconnected properly. And by that I mean properly, typically we're meaning we have negative feedback. And do we in this case? This is negative feedback, and this is now, because of that feedback, this is now a closed loop configuration or circuit. And its gain in this particular case the gain now is this. And what does that gain depend on? Does it depend on A sub OL? It doesn't, does it? It only depends on these externally connected resistor values, R sub F and R sub 1. And that's now closed loop. Questions on that? Question?
So if we're given an open loop, we might have to calculate the gain or something.
No, the question was, if we're given an open loop, are we going to be asked to calculate the gain? Probably not. We're not that worried about the open loop. You've been doing all your homeworks with closed loop, but a lot of times in the book he starts saying, assume you have a closed loop circuit, and you're going, I don't even know the difference between open loop and closed loop. I don't know what he's talking about. That's throwing me into left field. Don't worry about it. You can play in the left field, you can play in right field, you can play in center field. It doesn't matter. You just know that you're now in closed loop configuration, you're warm and fuzzy. We're going to be focusing on closed loop. I was just trying to explain that so that you don't feel caught off guard when you're reading the book. Let's now look at some analysis of a circuit. And let's look at a circuit that you maybe haven't seen before. Pardon?
On the positive negative configuration, it doesn't make any difference when we're finding gains if it's in there, other than just specified.
I'm not sure I'm understanding your question.
V sub D is still 0 whether it's positive or negative, right?
No, the question was, is V sub D, this differential voltage, 0, whether you have positive feedback or negative feedback? Is that what you're asking? No, V sub D is not going to be 0 when you have positive feedback. And if you enter saturation, V sub D is not going to be 0 either. So it's only when you're in well-behaved territory that V sub D is equal to 0, and that's your summing point constraint that you're assuming when you start your analysis, if you have negative feedback. Let's look at a differential amplifier. And this, if you want to go home tonight and study it, is page 698 of the text. And I'm simply going to talk about the simple configuration, which maybe doesn't have the nice physical characteristics that you might want in reality, but it allows us to at least talk about this analysis approach that you might want to be able to do, that you do want to be able to do come Thursday. And this is figure 1433, where we are assuming the ratios of these resistors are such that the ratio of R4 to R3 is equal to the ratio of R sub 2 to R1. Bless you. And here's the circuit. There's our op amp. We'll call that R sub 1. We'll call this one R sub 2. I think this is consistent with the book. And I could have given this to you, and I still could, I guess, on the exam and ask you to give me the equation for V naught. And if I'm asking for the equation for V naught, I'm expecting you to give me that equation in terms of input voltages, which are V1 and V2, and resistor values, R1, R2, R3, and R4. First thing, well, I'm hoping everyone has that copied down now, or you can not copy it down and look at the book tonight, or maybe you probably all carried your book to class today. So that's figure 1433. I actually do see some books. I'm impressed. The analysis. What's our first step in the analysis? Do we have negative feedback? And do we? And why do we? Because this R2 is connecting. That connects this V naught to the inverting terminal of the op amp. And that's all the justification you would have to supply on the test if you need to justify whether or not you have negative or positive feedback. Does that make sense? R2 connects, and it's now clipped off from my picture. There's R2. It's connecting the output terminal to the inverting terminal of our op amp. Negative feedback. That means that we can, if we need it, to help us, we can say, oh, that voltage, V sub D, which is defined to be from the non-inverting input to the inverting input, that small differential voltage, V sub D, is 0, based on the summing point constraint. Now what we want to do is to analyze this. We want to work from the input side, and we want to then eventually end up over here at the output side with our equations. And we probably want to start with some KVL, since we have voltages as our supplies. If we had currents, we might actually want to start writing a KCL equation at some node. But now we are probably going to want to write KVLs and then follow that up with KCL. Let me label some currents, and I'll label these so that they're consistent with the resistors, subscripts on the resistors. I now have 4 currents that I've labeled. Oh, something I keep forgetting, but you shouldn't. If we have no current going in, and let me call this I minus and this I plus, that's the current here and there. And what do we know with respect to the circuits we're analyzing in this class? I minus is 0 and I plus is 0. What does that mean about this guy? I sub x. What do we know about I sub x? It's coming out of the op-amp, which is a very good observation. May seem obvious, but what's not so obvious is what I haven't displayed. What have I not displayed? How we've plugged it in, the power supplies. We can have no current going into the input terminals and have current coming out, because we have power supply externally connected that's powering this. This is an active device. It's not passive. This is an active device. So we can have an I sub x coming out of that op-amp. That's coming from the supplies, the VCC and the VEE. That's supplying the current I sub x that comes out of that op-amp. And you need to make sure that you're comfortable with that. You can't do a KCL around that triangle unless you include the supplies. And then you really don't know what the supplies are. What you'll do is you will probably just say, you know what, let me find what I naught is. And if I know what I naught is and I sub 2 is, then I can back out what I sub x is by KCL. You could do KCL there if you wanted. I'm way ahead of the analysis, though. I don't want to be on the output side just yet. What I want to start with is, let's do a KVL here at 1. And what did I do? I didn't try to go up through V sub D across R2 and down to V naught. I wanted to drop immediately down so that I go from ground to ground rather quickly. And the reason I did that is so that I don't get too many unknown currents in my mesh equations before I have to start solving for. So here, step 2 is let's do KVL at 1. KVL at 1 says I have minus V1 plus R sub 3 I sub 3 plus R sub 4 R sub 4 equals 0. Questions on that? You're now experts with KVL, right? We've been doing it for however many weeks, 12 weeks. That's why you had to learn it, or we wanted you to learn it early. You have to remember it from now until the final, at least. And if you're taking the FE exam, on the FE exam. And if you're in an interview and somebody says, oh, can you find the input-output relationship of this op-amp? But sir, I'm a systems engineer. But I can do it anyway because I've had 207. Right? All right. Are we clear on that KVL? What do we also know? What do we know if somebody went up here and said, what do we know about that? What's happening at that circled black node that might help us? KCL. We can do KCL, and we know that I sub plus is 0. If I sub plus is 0 and it's leaving the node, I4 is leaving the node, I3 is entering the node, I3 must equal I4. And that's our note. We can say I3 is equal to I4 since this I plus is equal to 0. With that information, then, we can say that V1 is actually R3 plus R4 times I sub 3. Or we could solve for I sub 3 if we know V1, and if we know the R's, we can now figure up how big I sub 3 is, or what it is. We now have that current. Questions on that? This problem is a little bit different than a lot of them because I have things connected to the positive and negative that aren't just one of them going to ground directly. So this one's a little more involved or a little bit more interesting than others in the past. A lot of times at this point I would drop to ground. But I can't drop to ground because I'm not connected to ground just yet. So I have to go back through that R4 to get to ground. That's mesh 2. And what have I done? I've tried to work from left to right, going KVL, KCL. Now I'm doing another KVL. I'm alternating between those. And let me now write KVL at 2. So this is now, let's say, step 3. KVL at 2. I now go up into the negative terminal on the input V sub 2. I go across R1, which is now I1. Then I'm dropping down through V sub D, and I enter the negative terminal of V sub D first. So that's now minus V sub D. And then I start going down towards ground across R4, which is the voltage drop by Ohm's law, R4 times I4, and now I'm back to ground, now I'm 0. I can simplify this a little bit because of the summing point constraint. I know that's 0. And what else do I have? I can solve this for V sub 2. I can say V sub 2 is now R sub 1, I sub 1, plus R sub 4, and I could call that I sub 4, but I could also just as easily say that's I sub 3 based on what we've found up above. And I've now calculated I sub 3, if I wanted to, up here. And if I know V sub 2, I could then solve for I sub 1. I sub 1 is divide both sides by R sub 1 and isolate I sub 1. I now have V sub 2 over R1 minus R sub 4 over R1 I sub 3. But I sub 3, remember, was what I had up above, which was V1 over R3 plus R4, and now I have I1 expressed in terms of my input voltages, V1 and V sub 2, and these externally connected resistors. And now I could solve for I1 if I wanted to. That's probably not far enough, though, is it? Because I need to get an equation for the output voltage, V sub 0, and I'm not quite there. What if I, in anticipation of what I may need next, I'm actually going to want to do an output loop, and I could either go, well, if I had a ladder, I would get up and illustrate where I would go on that diagram. I'd walk around on that diagram, but here I'm going to have to do it on the board, so I might go this way. And that might be, well, I'm going to actually do a KCL right there first, and then I'll end up with doing a KVL around 5. The reason I want to do KCL at 4 is I want to relate I1 and I2. And I can relate those pretty easily because I know what I minus is. I sub minus. What is I sub minus? That's 0. Now I can do KCL at whatever I labeled it, let's say 4, and that says that I1 was going into that node, I2 was coming out, as was I minus, but I minus is 0 because that's going directly into the input terminal, and now I know that I1 is equal to I2. I can now do a KVL at 5, which is now minus V2 plus R1 I1 plus R sub 2 I2, but I2, well, I can substitute for that later. And that takes me all the way over to the output of the output side, and I can now drop down through V0 to ground, and I'm done with my KVL on the output loop. Question?
How would you choose to go to start at V2 rather than going to R4?
The question was a good question, and it was, why did I choose to go through V2 across to V0, and why didn't I go up through R4 and then go over to V0? I should be able to do either of those. It's just that I wanted to basically start with an input, V1 or V2, and end up with an output. But I do have I sub 4 already in terms of V1, and I could probably put all of those together if I went up that way also. It's just that I chose to do it this way. There are other ways to analyze the circuit. Question?
Sometimes in our homework it asks for input voltage, so right now there's 2 input voltages. So on the example we have to find an equivalent voltage.
Well, if in this particular circuit, the question was, on the homework, we were asked to find an input voltage.
I think so, something like that.
Maybe it was probably asking for input impedance. And if you have input impedance, then you need to know what's my input voltage over my input current. And you could possibly have 2 input impedances here at the 2 different sources. It's just difficult to calculate in this particular configuration. It's not laid out very well. That's why I said this is the simple case. The input impedance at the V2 input, it's not really valid to calculate. We can calculate the input impedance at the V1 terminal. I'm sorry, at the V1 inputs. And that's just going to be R3 plus R4. That's the current going in, and the current and the voltage at that point is V1. I wasn't going there, but I just did. Question?
You have to input voltages when it asks for gain.
So when you have 2 different inputs and it asks for gain, there could potentially be 2 different gains, one associated with each of the inputs. The way this particular circuit has been designed or created, we are going to see that the gain between V1 and the output and the gain between V2 and the output is the same, and so we're really going to get a difference between V1 and V2, which is why this is called a differential amplifier. We want to put a signal in at V1, another signal in for V2, which might actually be across your body, and this might be for getting an EKG, and there might be a huge 60 hertz signal on both of those that you don't want to have amplified, but you want to know what's your heart doing at these 2 locations, and you can then look at the difference in those voltages at the output V0, and that's maybe what you're interested in. And the common mode, which is this 60 hertz information, you don't want any part of that, and that's not going to get amplified. So you're going to have this common mode rejection big, or it's going to be really attenuated in this particular circuit. More than we really wanted to know, probably, but that's why this particular circuit is helpful or useful. Now that we have this, we know that I2 and I1 are the same, and I can now solve this for V0. V0 is equal to minus R1 plus R2 I1 plus V2. Or V0 is now V2 minus R1 plus R2, but what was I1? I1 was this, you could think of, mess. Didn't we have it up there? It's almost off the page, but it's this V2 over R1 minus R4 over R1 times V1 over R3 plus R4, and close the bracket. Now we have V0, our output voltage, in terms of input voltages V1 and V2. I'm going to let you go home and enjoy the algebra between this some algebra happens, and you end up with V0 is equal to R2 over R1 times V1 minus V2. And that's the difference amplifier input-output relationship that we were trying to derive. The gain, what's the gain in this circuit? R2 over R1. If I gave you tolerances on R2 and R1, could you tell me the range on your gain? That you need to be able to do for the homework. I'm sorry, for the exam. You've done it on the homework. You need to be able to do that. So if I said R2 is 100K plus and minus 1%, R1 is 10K plus and minus 5%, can you now tell me the range on the gain? You need to be able to do that on the exam. And that's what might be referred to as resistor tolerances. When I said it's on the exam, we woke up, huh? So I could say that R2 these resistors aren't all perfect, are they? If you say, oh, give me a 1K ohm resistor, you pull it out of a bin of 1K ohm parts, which you might have in your home hobby shop, right? You probably have all the resistors that you ever wanted. Oh, you don't have any, and that's all you ever wanted, wasn't it? Oh, you didn't have to say that. But if you had a resistor, let's say R2 is now 100K, and it's a 1%, or it's plus or minus 1%. And maybe now somebody says, oh, R1 is 10K plus and minus 5%. I would want you to be able on the exam to tell me what the range of gain you would expect out of this circuit to be. What's your nominal gain? The K's, which are 1,000, cancel. Those zeros cancel, and your nominal gain is 10. So you would expect your answer to be somewhere around a range that is on either side of 10. How would you find your maximum gain value? Is that okay? If you maximize your gain, you're looking for the maximum R2 value, which is 100K plus 1%. So now we're at 101,000. And what's the minimum R1? It's now 5% less than 10,000. Right? Which is, what is 1% of 10,000?
5%?
Well, I'm going to take 1% and multiply it by 5. I don't want to multiply everything by 5 just yet. What's 1% of 10,000? It's 100, right? So 5 of those is 500. This is now 10,000 minus 500. 9,500. And that would be your maximum gain. Is that okay? And then what would be your minimum gain? You don't have to tell me. You just have to show me how you would find it in today's lecture, but on the exam you better be able to calculate it. It might be one of the answers. And it may not be. It may no answer, whatever I call that. No answer available, NOA.
Put that. No answer should be NOA.
NOA was actually one of the choices this exam, and you should have circled it. In exam 2, not exam 3. I don't know what exam 3 is going to be. But this is going to be minimum of R2 over max of R1. Tolerances. You should be able to do that.
Can we go back to the equation? Because it doesn't make sense that it's not dependent on R3 or R4.
We moved off of that 5 minutes ago. The question was, why is our gain not dependent on R3 or R4? Pardon?
Isn't R2 over R1 defined as R3 over R4 equal?
Can somebody answer this question simply? Some algebra happens. That's for you to go home and enjoy, but really what you're remembering is this relationship. We assumed that those ratios were in existence, that R4 over R3 was the same as R2 over R1. If we make that assumption, do the algebra, the R3s and R4s go away. But yes, they would generically be involved in your expression. But because of that condition right there, and that you've now enjoyed your algebra, those fall out and you just have R2 over R1. Does that answer your question? Murphy's Law. What is that?
If you can plug something in backwards, then
If something can go wrong, it probably will go wrong. What can go wrong in these op amps?
They can show up on exams.
The op amps can show up on an exam, and they are going to show up on the exam, and you won't have three-phase power on exam number 3. I didn't mention that, but I was implying that with it not being on the list. So just concentrate on chapter 14 for Thursday. And if you want some background material, that's in chapter 11, section 5 and 6, to talk about impedances and amplifiers. What are some practical considerations? We've already talked about saturation. Is it clear how that comes into play? If I state that verbally, this can occur when the output, whoops, Saturation can exist or can occur when the input voltage and the amplifier gain and when I'm saying the and, I'm meaning their product. So can occur when the input voltage and the amplifier gain product exceeds the supply voltage values. And what are the supply voltage values? Those are VCC and VEE. Are we exercising, or was that a question?
Is it also current?
I'm going to get to current. That's why I said this is a 3-hour lecture. Okay? So here's our example for the, do you want to see an example of this, or do you want me to just state the current? Example? Here's an example. Suppose that we have the following circuit. Minus plus here's V naught and let's say this is V sub EE, this is V sub CC, here's R1, R sub F, and Vn. Let's make some assumptions. Let's assume that VCC is plus 10 volts and VEE, let's say, is minus 10 volts. And if we are operating in the linear range, or if we have no saturation, how is the output related to the input? And now you should be able to just do this in your sleep. This circuit, right? This is a basic, well, first, what have you already done? Convinced yourself that there's negative feedback, correct? There is negative feedback. It's going from, and it's offered to us by R sub F. It's connecting the output to the inverting terminal of our op-amp. Negative feedback. If no saturation occurs, what's our formula for the output voltage in terms of the input voltage? That's what will happen if we have no saturation. Let's suppose, and remember, this was under the heading of Murphy, and I won't give you that heading on the exam. You'll have to figure it out. Suppose R1 is 1K, R sub F, let's say, is 100K, and let's say that Vn is equal to 600 millivolts, or 0.6 volts, or 0.6 of a volt. The question is to find the output voltage, V naught, and Vd. On the exam, you would say, okay, well, I know that equation for my relationship between the output and the input, and I know my output resistor and my input resistor, they're different, or that gives me a ratio of 100. My output voltage then is minus that ratio times my input voltage, which is the 0.6. I now have minus 100 times 0.6, or minus 60 volts. And what I want you to be doing on the exam is questioning your answer or answers. and say, is that output possible? And so what are you doing? You're actually comparing this output to your supply voltages. Your supply voltages were plus and minus 10 volts. That's what's powering your toaster. That's what's powering your op amp. You've now, based on no saturation, you've concluded, oh, if I do not have saturation, this particular circuit with this input is wanting to put out minus 60. That poor op amp just can't do it, can it? It's only being powered with plus and minus 10 volts. What's the output going to be? It wants to go all the way to minus 60. It's trying to get there. It shuts off at minus 10. Question?
If the difference between VEE and VCC were the same, but it was like negative 20 and 0, what would the output now be? 20, negative 20 volts?
So the question was, what if V sub CC was 0 and VEE was minus 20? What would my output be? Negative 20. This is now the answer that you would want to circle. And if none of those are listed, it would be NOA. None of the above. Question?
Is there any way to check whether it's not
Is it possible to check if I do not give you the VCC and the VEE? Any answers? It's really not possible. You would have to say this seems a little large based on what problems I've worked so far this semester. And if I have a pretty large supply voltage of plus 15, minus 15, this is still going to exceed that. So I'm going to be stuck at one of those values. And in this case, it's an inverter. I'm stuck at minus 15. And you could say that, for example. What we haven't done, and I'm not sure that I'm going to do it, is what is V sub D. Now we're in saturation. Now the summing point constraint has been violated, and we could possibly have a non-zero V sub D value. Meaning in our circuit, we had this. Now we know this is minus 10. Is that what we said? This was 100K. This was 1K. Here's Vn. What was Vn? It was 0.6. We've now figured out that we're at the rail. We've saturated. This VD is no longer necessarily equal to 0. And that means that this voltage right there is not at ground. This is now at some V sub x, which I hope by this point it's clear that V sub x is, if you did a KVL, you would say minus V sub x, minus V sub D is equal to 0, or V sub x is minus V sub D. They're just the negative of each other. And I'm hoping that you can see that you could write KCL here and say there's I1 and here's I2. I1 is equal to I2 because you still know that current going into the negative or the inverting terminal is 0. That I sub minus is 0. This guy right there, I minus, is still 0. I1 is equal to I2, and we can solve for I1 and I2, but based on all of these, the only unknown is V sub x. We can solve for V sub x and figure it out. Question? I'm sorry? Would I plus be 0? Is this current What's it? It's still 0 also. In our op amps, we're going to have the input currents going into our input terminals is always 0. We could have current coming out, because where is that coming from? That's coming from our toaster that we haven't shown, the VCC and the VEE. Questions on that? Question?
Can you explain where you get the X from again? Or you just draw it there?
Why did I just draw V sub x there? Because I knew that it would make me feel warm and fuzzy if I labeled what that voltage was. I feel more comfortable now if I say there's a V sub x right there. That's at some potential. If you had a multimeter, you would connect maybe one of the ground lead to ground, and then you would start probing with that other positive lead. And if you put the probe at that particular node or at that junction, you're going to measure a voltage. It's not going to be 0 because now you've saturated.
Or you can just call it V sub D and the sign is already reversed there.
And you could call it V sub D and the sign is already reversed if you wanted to. But for some reason I didn't want to think that way. I said, you know what, I want to just call it V sub x or V sub 20. I just wanted to call it something and solve for it. And then I know that that's the negative of V sub D based on a little KVL. That's the only reason I did that. Let's look at another Murphy, which is limited output current. And I don't think I'm going to get all the way through this, so let me just go through my note. And I think I've just stated this, but I want to make it very clear. Even with no current into an op-amp's input terminals, a current can flow out its output terminal. That is because of bless you. What is I plus? That's 0. What's I minus? 0. What's the input impedance? Infinite, because we have Vn divided by 0. So our input impedance is infinite. What is this circuit? It's negative feedback. What does this VO equal? Could I do a KVL? Could I simply do this? Could I do this? I have now minus Vn plus V out is equal to 0. V out is Vn. What is this called? A buffer. Why would we want to do that? Why don't we just do the following? Here's V in, here's V out. Why don't I just connect them with a wire?
Set the max to
I can have a maximum, but the main thing is I want V naught to be Vn, but I like the fact that I have infinite input impedance. I'm not going to have that with just a wire. But the reason why, the whole reason that I was wanting to talk about this is this VCC and VEE are plugged in. We have this op amp plugged in. That's why we can get this current coming out, I naught, that's something other than 0, even when I plus and I minus are not. I'm out of time and I have something to hand back if you want it.